Okay, guys. Well, thank you for joining me this Friday afternoon for our session on SBAs in medical statistics. My name is Niko. I'm a P here at St. George's, and I'm also an honorary research fellow at Imperial College. And we're just going to be having a look at some of the statistical questions from the Quesmed question bank, which I'm sure you're all very familiar with. So what I'm trying to do today is I'm trying to go through like the basic stats that you will need to know for medical school. And I think looking at medical students and also graduate doctors, I think that it's one of the areas that causes the most confusion. And also I think medical students don't really enjoy it. But I think it's such a high yield area because at least in my medical school, we get both SBAs and also short answer questions on statistics and research. And the amount you need to know to be able to get those questions right is very small, and they tend to represent kind of like 5 to 10% of your mark. So probably out of any other topic you could study in your revision, this is probably the highest yield because you just learn this stuff and you'll be getting an extra 5, 7, 10% in your exams. Now, as I said, the Quesmed question bank is my source for the SBAs. And some of the questions will require some calculation. So if you have your phone or your laptop, get the calculator out. There's only going to be a few. I'm not sure in various medical schools whether they expect you to do calculations, but if they do, they will give you a calculator, or they'll be really simple. So yeah, without further ado, let's go on. So one of the issues with statistics as compared to other topics in medical school, and I just want to talk a little bit about the philosophy of statistical thinking, is that in medical school, we're very much taught what is considered system one thinking. And what this means is that you make associations based on words, based on presentations. It's very quick. It's, you know, if I say to you, bilateral hilar lymphadenopathy, you're saying sarcoidosis. You're connecting those two words. It's really quick. You get it from your memory, and it's very fast and efficient. Whereas you have this other method of using your brain, which is called system two, and this is more to do with calculating, understanding the underlying concepts, and understanding really what the principles are of what you're observing. And this is really important because medical students are used to learning in a sort of black box way. You get information, you put it in, and you get other information out. And it's really bad to learn statistics like that because it's impossible to memorize all of stats because it's calculating. So what I'm going to try and do today is open this black box and kind of make you understand not only how to calculate things, but also what it actually means in the real world. So this is just a list of topics that we'll be going through. Pretty much everything you need to know at medical school, most of the statistical stuff, and a little bit on study design and biases, which are SBA favorites. So I'm going to start off with an easy MCQ. I've been told that you guys don't like me reading out the question, so I'll give you a little while to read it, and I'm sure Sav will raise the poll in a bit.
Okay, so 15 seconds remaining. Five seconds.
Interesting. So we have a little bit of a split here. 68%, so the majority of people went for CTPA, and some people picked a D-dimer. Okay, so the answer to this is D-dimer. And the people who picked CTPA might be very upset with this answer, but I want you to have a little look at this specific word. And this question is designed for two things. First of all, always read the question carefully, because the classic medical school question actually asks you for specificity. And number two, you need to understand what this actually means. And just to prove my point, from some papers, here are the sensitivity and specificity values, and you're not going to be expected to know these values, but this is just to illustrate a point of how important it is to understand what the question is asking you. And as you can see here, the sensitivity of the D dimer is actually much higher than the CTPA. The specificity, however, is much lower than the CTPA, which is why the CTPA is the preferred method of investigating the PE. And I'm going to use this as a segue into sort of having a look at sensitivity and specificity and how we can calculate these. So let's go on to our next SBA. Now, this is one of the ones that you might need your calculator out.
Okay, so I'll be releasing the poll in the next 5 seconds to get all the numbers you need down.
Please do let us know in the chat if you need longer to calculate the numbers.
Okay, and 15 more seconds. And 5.
Okay, so we've had a bit of a range of answers here, with the slight majority in B. We've had some people for D and some people for A. Okay, so the correct answer here is B. And don't worry if you got this wrong. These kind of questions are quite tricky, and it's always a bit tricky to understand what you need to do. But I'm going to talk you through how to calculate it. So specificity and sensitivity are like two favorite words that people throw around, and they're very common. And you know, I've been doing research for years, over a decade now, and I still use this method of drawing out this box to make sure that I don't get it wrong. So what we're going to do here is we're going to populate these quadrants of this box with information given to us in the question. And Quesmed have been very kind to us by actually giving us a table like this. In many other scenarios, this information would actually be hidden within the text. So if we just look at, first of all, at the people who actually have the virus, so looking at the first column, we can see here that 104 people have the virus and also tested positive for this disease. Now, we call this group of people the true positives, people who were correctly identified as having the virus by the tests. Now, in the same group of people who actually are diseased, there's also these 26 people who actually, they were missed by the test. So even though they have the disease, they tested negative. And we can calculate the sensitivity by dividing the number of people who tested positive and have the disease by the overall number of people who have the disease. So 104 plus 26, so we know there are 130 people with the virus, and then we divide this number by this number to get the sensitivity. Now, the previous question was actually asking you for the specificity, but I'm just telling you the sensitivity first, as it's the first column. Now, for the second column and for the specificity, we have a look at the people who are actually healthy and don't have the disease. So in this group, we can see that 65 people tested negative while being healthy. which is good. That's correct. These are the true negatives, people who are correctly identified as being healthy. However, unfortunately, in this group, we also had 35 people who, despite being healthy, were shown up as having the disease by the test. So 35, these are the false positives, people who were incorrectly probably taken off into hospital, told to have extra examinations and invasive procedures and given medication that they didn't need. So the number of true negatives divided by the total number of healthy people is the specificity. So when you're drawing out this table, you divide this number by the total of the whole column of this plus this. So it's 65 divided by 100, that's 65%, which kind of makes sense. That was an easy calculation. So remember, when you're drawing out this table, the sensitivity and specificity are calculated downwards through the columns. And this is what this arrow is meant to represent here: specificity and sensitivity. And that's how you calculate these. And numbers. So when you're reviewing the slides, you can see where I got these numbers from, so to make it absolutely clear. So I want to talk a little bit about, like, conceptually what sensitivity and specificity mean. And to do that, I'm just going to go back to the D dimer, just talk a little bit more about this. These are really important statistics because the reason we don't use the D dimer is, even though it's got a high sensitivity, and what does this mean? This means that if you have a PE, you are 99.5% likely to have a positive D dimer test. So almost everyone who has a PE will come positive on the D dimer. However, with its low specificity, this test is going to pick up a whole bunch of people that actually have something else, or maybe have nothing at all. So this is why the D dimer is actually a pretty poor test for the PE, because you're going to be treating loads of people, I don't know, giving them anticoagulants or thrombolytics, even though they shouldn't be having them. Whereas the CTPA is very good at telling you when you don't have a PE. So 69% specificity. That means that if you have a positive CTPA, sorry, if you have a negative CTPA, you're very, very unlikely to actually have a PE. So it's a much better test because we're not treating people unnecessarily, if that makes sense. And I've put the definitions of specificity and sensitivity here for you guys to peruse in the more formal definitions. That makes sense. So before I move on, is everyone on board with sensitivity and specificity so far? If you have any questions, please put it in the chat or the Q&A. I'm keeping my eye on it. Doesn't seem like we have any questions. Okay, so I'll move on. So this is our next SBA. And this is about positive predictive value. This is another one that probably needs a calculator, so whip that out if you have it.
Okay, I'm going to be releasing the poll in 5 seconds. There you go. And 20 seconds remaining. Ten seconds.
Okay, so the overwhelming majority went for E. A couple of other questions on that as well. And well done. Almost everyone got this right. And I just want to go through the calculation of this just to make sure everyone's on the same page. Again, as I said, this box will help you so much with these test statistics. You know, I still use it to myself. I get my pen and paper out and write everything down. So the way we calculate this is actually, if you remember, specificity and sensitivity were going downwards, the predictive values are actually going across. So if we have a look at the, again, Quesmed have given us a nice table here. If we look at the positive tests, so we're looking at just the people who tested positive, we can see that 168 people have rheumatoid arthritis and tested positive, whereas we have 28 people who tested positive despite not having rheumatoid arthritis. Okay, so the total number of people who tested positive is just the sum of these two boxes here, which is 196. So to calculate the positive predictive value, what we actually do is we divide the number of true positives by the total number of positives. So as you can see here, you divide this number by the total which we just calculated. And using a calculator, you know, we can figure out that that's 0.857, which is 85.7%. And that's how you calculate the positive predictive value. Just to point out, we don't use this column in the positive predictive value, sorry, this row in the positive predictive value, we use it in the negative, and we'd calculate the negative predictive value in exactly the same way. And that's just explaining what these numbers are here. So again, I want to talk a little bit about, like, philosophically what these terms mean. Now, the positive predictive value is just the percentage of people who had the disease of the people who tested positive. So we take all the people who tested positive, and of those, how many actually did have the disease? And the negative predictive value is basically the same for the negative results, and that is, of the people who tested negative, how many actually didn't have the disease? And what we actually want here, we want these numbers to be as high as possible to make sure that, you know, out of the, how many was it, 196 people that we sent off for further investigations, as many of those were actually diseased, and we're not giving, you know, unfortunately, these 28 people were getting inappropriate investigations or treatments. And just for completeness sake, the calculation for the negative predictive value, which would be using these two columns here, is 80.4%. But it's calculated in the exact same way. You just add these two together and then divide the true negatives by that sum, if that makes sense. And that brings us to the end of positive and negative predictive values. Before I move on, is everyone still with me? Is everyone on board? Does everyone understand? Are there any questions? Nope, I'm not seeing any questions, so I guess I'll carry on. One thing I just did want to point out, because sometimes the terminology can be a bit tricky, is just type 1 and type 2 error. And these are just different names for the false positives and the false negatives. So type 1 error is the people who were unfortunately tested positive even though they didn't have the disease, and type 2 error are the people who had the disease but were missed by the test. And to help you remember which is which, and this is how I remember it, is I just look at these words. Sorry, this is a bit childish, but so false positive, right? So this designation here actually has one bad word. So false is the bad word, positive is the good word. So type 1 error has one bad word, which is the false, whereas type 2 error has two bad words, false and negative. So both false and negative is bad, therefore there's two of them, type 2 error. I'm just going to take a moment to look at this question. Could you quickly distinguish between positive predictive value and specificity? Yes. So specificity is looking at the proportion of people who were correctly identified as not having the disease. So we look at this column. These are people who don't have RA. Specificity is this number divided by the total people who don't have rheumatoid arthritis. Okay, so you're actually, like, if you want to think of it visually, it's looking at the row. And what this number signifies is how good is the test at correctly telling you you are healthy. Whereas the positive predictive value is looking at what proportion of people of the ones that tested positive actually had the disease. So in this case, it would be out of all the people who tested positive, which are in this row, what proportion of them actually had the disease, which is 168. So don't forget the predictive values are the rows and the sensitivity and specificity are the columns when you're drawing out this box. Hopefully that answers your question. And if there's no other questions, I'll move on from this. So I just wanted, again, to kind of think holistically about what the stats actually mean. And I hear the term statistically significant thrown around a lot by a lot of people. And people tend to get to statistical significance, you have to do an experiment, right? And complicated definitions of type 1 and type 2 error are the rejection of a true null hypothesis and the non-rejection of a false null hypothesis. And that kind of doesn't really make sense, because before you even try to detangle what these words mean, what is even the null hypothesis? And actually, if you Google what the null hypothesis is, you'll get a complicated explanation from Wikipedia. You'll get complicated explanations from, like, actually Fisher and his friends were the ones who developed t-tests and, like, the student t-tests and stuff and statistical significance. But the definitions are very complicated. And I just want you guys to think about how experiments are set up in research. So let's say that I wanted to do an experiment to prove that the Earth was round. The way science works is I don't actually set up an experiment to look at the roundness of the Earth. I actually hypothesize that actually the Earth is flat, and then I kind of set out to disprove the opposite of what I believe. And this kind of false bad hypothesis is effectively what the null hypothesis is. And the goal of statistics is to reject the null hypothesis and therefore point towards what you actually believe. And I know that's a little bit convoluted, but it's this whole proof by contradiction, which Fisher talks about. Now, why am I telling you all of this? It's because all of this statistical significance is actually expressed by a p-value. So you must have read papers or heard, professors and scientists talking about, oh, p-value 0. this, p-value 0. that. And again, if you look at what the definition of a p-value is, you're going to get a complicated definition like this with odds ratios and unities and populations, and I think it's quite conceptually hard to grasp. So the way that I want you guys to think about what a p-value actually is literally the percentage chance that the experiment we did was wrong. And it's so much simpler when you think about it like that. So when you look at a p-value, so I did my experiment about the roundness of the Earth and I got a p-value of 0.01. What does that mean? That means that there was a 1% chance that the results of my experiment were wrong or random. Well, random is wrong, so you guys understand what I mean. And that is the simplest way of thinking about p-values. This, however, brings up another question. Why is the statistical significance cutoff 0.05? And literally, it's arbitrary. Someone at some point decided that a 5% chance that the results of your experiment are wrong is fine. And we calculate the p-value through different statistical tests, the t-tests, ANOVAs, multivariate statistics. It doesn't really matter, for the sake of this webinar, how we're calculating the p-value. I just need you guys to understand what the p-value means, because in a lot of, this is more for short answer questions, they might ask you, what is statistical significance? So anyways, moving on from that, still relevant to statistical significance, are confidence intervals. So I want you guys to have a look at this SBA. think the poll's been sent. Oops.
Okay, and 5 more seconds.
I mean that. So I'm not sure if that caused some distortion. But there we go. Okay, so the majority of people went for answer D, and that is the correct answer. And I'm very happy that people went for this answer, because a lot of the time I think people get confused with other definitions of the confidence interval. And I want you guys to just understand that it's a measure of certainty, not of probability, which is what these some of these other ones signify. If there's anyone who wants a more detailed explanation, just pop it in the Q&A and I can go over confidence intervals in more greater detail. But it's just a range of values where we are 95% certain that the truth lies within those two values. Just bear in mind that I did copy this off Quesmed, but this is the definition of the 95% confidence interval. You have other ranges. You have the 98.5 and the 99 point something confidence interval. So there are different ranges of certainty. Okay, on to the next SBA. This is another one that might require a calculator.
Okay, releasing the poll in 5. Last 5 seconds. Actually, maybe I'll give you 10 seconds. Not many have voted yet. Okay, so 5 more seconds. Okay.
Okay, so we have the majority of people going for answer A, and a few people in the various other answers. And this is quite a tricky question. I actually think fewer people answered this than the previous ones. It's a bit tricky, I'm not going to lie. So the answer here is 3.2, and I think I'm going to go through how you get to that number after just replying to one of the questions from the Q&A. So in terms of the confidence interval, just so I'm not missing the questions, how are they calculated? So there are various ways of calculating the confidence interval. It really depends on what you're measuring, the type of variable it is, what metrics you're using. It really varies. The simplest way of calculating it is using standard deviations, but you then have to prove that your population is standardly distributed. So it gets really tricky and complicated. In general, for medical school, it's more important to know what it means rather than how you get to that number, because confidence intervals could have been an hour lecture by themselves. So in terms of the confidence intervals for risks and ratios, we're going to actually cover that a bit later on. So just hold on to your question. We'll go over that bit in the future. Now, going back to this and the relative risk. So going to this. So it's really important with relative risk and odds ratios to understand what the event is and what the exposure is. Okay, so before I explain how you get to the relative risk, I want to also check that you whether you guys know how to do the odds ratio, which is what the next SBA is on, and we'll get onto how to calculate both of them in a second, because there tends to be a bit of confusion between the two. So on to the next SBA.
Okay, releasing the poll in 5. And 10 more seconds. Okay.
Okay, so we've had a little bit of a spread of answers here. And again, this is a tricky one. Both of these are quite tricky and require a bit of calculation as well. But the majority of people went for B, with a few other answers here and there. Okay, so the answer here is B. And I'm going to go step by step, I think, based upon the answers through how we get each of these. So first of all, the ratios. The risk ratio and the odds ratio. These are two values that you're going to see a lot in medical literature. And so they get confused a lot. They're also sometimes used interchangeably, which is just wrong. And the reason is, I think it's because you see them both in like meta-analyses. But I just want to highlight a few things. First of all, the risk ratio is actually to do with probability, whereas the odds ratio is to do with odds. And I'm not sure if any of you ever go to the bookies and bet on horses or the football or anything like that. But these are two very different concepts. And the thing is risk ratio is technically slightly more powerful, but because it gives you slightly more information, but you have to know the incidence of whatever it is you're measuring. And in the case where you don't know the incidence, and we'll go through what incidence and prevalence is later on, you have to use an odds ratio. So I have like these tables here to just kind of show you step by step how to calculate these. So with the relative risk, well, first of all, as I said, you have to identify which is the exposure and which is the event. Now, in this example here, the exposure is smoking, whereas the event is lung cancer. So to calculate the relative risk, the risk ratio, you first calculate the probability of someone who's a smoker, therefore exposed, has of contracting lung cancer. So you do this number here divided by the sum of these numbers. So you look at smokers who contracted lung cancer, divide that by smokers in total. And then you do the same for non-smokers, and then you divide those two ratios. And that's how you get the risk ratio. So going back to our original question, do you know what? I wonder, can you guys see my calculator? Is that showing up, Sav?
Yes.
So let's just actually calculate this so we can see what we have. So first of all, we need to identify which is the exposure and which is the risk. And this is where a lot of people trip up because they start messing with the wrong numbers. So here, the actual exposure is the asthma. The disease is actually the exposure, because what you're looking at is which is the outcome, the reaction. So you're looking at whether having asthma influences whether you're going to have a reaction or not. So then, first of all, we look at the exposed group. So the exposed group are the people who have asthma. And you say, okay, out of the exposed group, how many people got a bad reaction? So that's 54 out of the total of this. So that's 87? Yes, 87. That's 0.62. So remember that number, 0.62. That's the probability of having a reaction while also having asthma. Then you look at the same thing for people without asthma. So that's 23 divided by, I think, 118. And that's 1.94 or whatever. So what we're going to do now to get the ratio is we're going to divide the first one by the second one. So that's 0.62, I think we said, divided by 0.19. And that gives us 3.26, which, you know, I didn't put the long numbers in, so that's close enough to 3.2. And that's how we got that for this SBA, if that makes sense. I'll close that calculator there. Now, for the odds ratio is basically the same thing, except in the bottom part of the fraction, we don't add them together because this is an odd instead of a probability. So in this case, we just divide the number of people who have the event, who get lung cancer, by the people who don't in each of the exposed and non-exposed group. And that's how we get this odds ratio, if that makes sense. And again, I'm going to calculate it for you guys, excuse me, with the SBA here. Just to clarify again, you have to identify what the event and what the exposure is. So the event here is having a migraine, whereas the exposure is the calcium and the vitamin D. So in this case, you just divide 21 by 29. That's 0.72. And then we look at the other group. That's 129 divided by 234. Oh crap, what was the first one? 0.55. Sorry, let me just redo the other one. 0.55. Okay, and we'll divide that by 0.55, and we get 1.3. Therefore, the answer is B. So hopefully that clears up those calculations. And if you need to look through the slides again, just have a look at this slide, and it will explain to you exactly how you get to each one of the numbers. Now, going back to the question one Anonymous asked about whether there is anything that we can infer from the confidence intervals and the odds ratios, it kind of comes down to this, that first of all, the higher the odds ratio or the risk ratio, the more strong the effect of that exposure has to the outcome. However, if that ratio is 1, then it means that exposure doesn't have an effect. Okay? And this is really important to understand, that if it's 1, there is no effect. Oh, and this is just to reiterate the point that you have to identify what the event and the exposure is in these tables, because as you can see here, Quesmed have actually transposed these. So in the first case, the exposure is the asthma, and that's the columns, whereas in the second one, the exposure is the calcium supplements, and that's on the rows. So you have to make sure that you're dividing and adding the correct numbers so you don't get the wrong result. Has everyone kind of grasped that? I know there's quite a lot of information there, but looking at that summary slide, this one gives you all of the information you need really for the ratios. Anyways, let's go to the next SBA, and this is kind of like bringing together confidence intervals, odds ratios, statistical significance, everything together into one SBA. So I'd like you guys to have a little look at this. And just to add to the point about whether a confidence interval is better when it's larger, it's hard to say, but in general, if your confidence interval is wider, it means that there's more uncertainty in your results. So I'd prefer a narrower window. Oh, crap.
Okay, releasing the poll in 3, 2, 1.
Sorry, you might have seen the answer there. I was trying to scroll through the answer, the questions. Would you be able to explain why odds ratios are easier to use in meta-analyses? Odds ratios are not easier per se to use. It's just if you don't know the incidence of whatever it is that you're testing, you have to use an odds ratio. So in a sense, they are easier because they require less information, but then as a drawback, they give you slightly less information. The next question is, when you have the option of feasibility of feasibly using both odds ratio and risk ratio, which would be better? It kind of depends on your study design, but I personally, if I can calculate a probability, I will calculate the probability. It's slightly more strong. It lends a bit more weight to your argument, if that makes sense.
Okay, so closing the poll in 3 seconds.
Okay, so let me not do that. So the answer here is smoking, which is what the majority of you people actually picked. A few people picked family history. Now, I can understand why people picked family history. So let's go through these answers one by one. First of all, gender is out of the question because that's not even something that was tested here. So E, never mind. Now, out of the other 4, what we said previously is that the stronger the correlation, the higher the odds or risk ratio will be in your statistical analysis. So then one would think that the most important risk factor would actually be the one with the highest odds ratio, which would have been family history. However, there's one important thing which I mentioned previously, which is that if the odds ratio is 1, there is no effect. And if you couple that with the idea that the confidence interval gives us a range of values in which we are reasonably certain that the true value lies, then what you can infer from that is that if the confidence interval crosses over number 1, the number 1 therefore is less than 1 in that case, we can't be sure that that particular risk factor is actually having an effect. So I've highlighted this here. So you see how this is 0.9. This means that on the lower end, the actual odds ratio for family history could be 0.9 or it could be 1. Therefore, it's possible that family history has no effect on whether you're going to have a stroke or not. So through this, we can infer that actually the results of this analysis for the odds ratio for family history is statistically insignificant. Therefore, this is not a valid result. Neither would this be. Well, this was not a valid result to begin with because it's lower than 1 anyways, but we don't know whether it has a positive or negative effect. So both family history and socioeconomic level are out of the picture. This would leave us with only this, smoking, and history of head trauma, with the range of values not intersecting 1 as the only 2 possible candidates. And of these 2, we're going to pick the one with the highest odds ratio, which, as correctly most of you identified, is smoking. I'm just going to have a little look at the questions. Okay. In odds ratios and in risk ratios, if the 95% confidence interval crosses 1, does that make your result any less significant? Yes, as we just said, if the confidence interval crosses 1, it makes your result statistically insignificant at the p equals 0.05 level. If we were accepting that cutoff, then it's statistically insignificant. If you have all four values in that table, would you not be able to get the probability? So yes, if you have an idea of population incidence, because depending on your on the design of your study, so looking at this situation, if you're doing a cross-sectional study, which we'll talk about later on, where you're just taking a slice of information at a particular time, you don't know how the values of people without asthma, without the event are fluctuating, if that makes sense. Therefore, you don't know the incidence. You don't know how many new people are coming into the pot, into that barrel. And if you don't know how many new people are coming into that barrel, you don't know how the change of the numbers you're seeing relates to the risk factors. So I see what you're saying. Mathematically, you could still, like if you had all four values, you could calculate it, but that would not be a validated result if you can't say for sure, you know, every year we have 100 new cases of cancer or of adverse reactions or of migraines, if that makes sense. Okay. Can you go through how to choose risk ratio or odds ratio for meta-analysis? As I was saying, if you do not know the incidence of what it is you're looking at, so let's say here we don't know the incidence of lung cancer, then we wouldn't be able to use the risk ratio. We'd use the odds ratio. Another reason why you might use the odds ratio for a meta-analysis is if there is a mixture in your primary literature. So if some of your primary literature uses risk ratio and some of it uses odds ratio, to keep the data homogeneous, you would pick the odds ratio because you can infer that from the risk ratio, but not the other way around. A larger odds ratio means that there is a greater correlation between your exposure and your event. So in this case here, a larger risk, either actually, a larger odds ratio for smoking means that smoking would have a bigger effect on whether you get lung cancer or not, if you're comparing, let's say, smoking and obesity. Isn't saying that we are 95% sure that the true risk ratio is within a certain range different from determining whether this risk ratio is significant. I am very confused. I am sorry I have confused you. I'm going to try and re-explain what I've been saying. So, if the confidence interval for an odds or risk ratio contains the number 1, so it goes from so something from below 1 to something above 1, then we can infer, because what we're saying with this confidence interval is that we're 90% sure that the true odds ratio is between these numbers. There is a chance that the true odds ratio for family history is 1 or is less than 1 because the range goes below it, right? Because there is a chance of that, and we've defined anything as that has less than a 5% chance as statistically significant, and anything that has more than a 5% chance as statistically insignificant, we can infer that for family history, it is the family history is statistically insignificant when it comes to the risk of stroke. Does that answer your question? If it doesn't, I can go through it again. Can you explain how you interpret the risk ratio or odds ratio? What does the 2.3 mean in the question? So the easiest way of thinking it is that you are 2.3 times more likely, technically no, but it's a good way of thinking about it, more likely to get a stroke if you smoke than if you don't smoke. And this result is statistically significant. So you have a two-step process. First, you interpret the odds ratio, and then you check that if the odds ratio is statistically significant. So number one, we can infer that smoking increases your risk of stroke by 2.3 times. And then that is a statistically significant result because of the confidence interval. The family history does not pass the confidence interval checkpoint because it passes one. Did I say that risk ratio can be used in cohort studies regardless if incidence is known? No, you need to know the incidence to use the risk ratio. If you don't, you have to use the odds ratio. And NY, I did say that the family history is statistically insignificant. Yes, because the confidence interval passes the number one. We can safely infer that given the information given in this question. So I hope that answers all of your questions. If you have more questions, please do pop them in the Q&A, and I'll try to clarify any points of confusion. Yes. So just to talk about incidence and prevalence, because we've talked a lot about these in regards to odds ratios. So I'm just going to give you a little sort of picture to kind of illustrate how I think about incidence and prevalence. So in this barrel, this water represents all the people that are suffering from a specific condition, let's say lung cancer. And then every so often, let's say once a year, I come and I pour in a jug of more water. And then obviously, because this is a disease, out of the tap on the other end, you know, some people are cured, some people unfortunately die. And using this idea, we can understand what incidence and prevalence is. So prevalence is the amount of water that's in the barrel, therefore the amount of people that have lung cancer at any point in time. I've taken a picture and I'm looking at the barrel. Whereas incidence is how much water I'm pouring in. And if I pour in 1 jug per year, that incidence is annual. If I'm pouring in 1 jug per month, that is the monthly incidence, if that makes sense. I think most people understand what these two terms mean, but I thought I'd clarify just in case anyone had any confusion. So let's go to the next SBA. And this is actually going to be a multi-step SBA based on the same information. So here we need to calculate the relative risk reduction.
Releasing poll in 5 seconds. And 15 seconds left. 5 seconds left.
Okay. Oh, actually, let me not do that. So some of you have gone for E, some of you have gone for B. Okay, well, the answer here is E, and I completely understand why people went for B, because looking at basically this is asking you to look at how good this new yazepine drug is at reducing deaths in heart attacks. And the mortality rate here goes from 20% to 15%. So you could say that the difference is 5%, but that's not the relative risk reduction. The relative risk reduction is comparing this number to this number. And when you compare these two, to go from 20 to 15, that is a reduction of 25%, if that makes sense. So you went from 20 to 15, and that is a relative reduction in deaths of 25%. I guess an easy way of calculating the relative risk reduction, if I can just show you with my calculator, is you just to show you how you can, because sometimes the numbers aren't simple as this, you just get the first number, like this one, the lowest one, divide that by that, and then, so the original number, and then you minus 1 from that. And that gives you 25, so 25%. So if I went from 20 to 10, I would take 10, divide that by 20, and then minus that by 1. So the relative risk reduction would be 50%, if that makes sense. Okay, so we can go on to the next question. What is the absolute risk reduction? Based upon the same information given. And I think here you guys will see where you went wrong last time.
Okay, releasing the poll in 5.
So I'm just going to answer a question in the meantime. Why can the risk ratio be converted into odds ratio but not vice versa? Well, it kind of depends on the information you have. It can be if you know the incidence, but typically one of the main reasons you do an odds ratio is because you don't know the incidence, and if you don't know the incidence, you cannot calculate the risk ratio, or it wouldn't be a valid result at any rate. You need to know the incidence. Yep, so pretty much everyone got this, everyone went for B. So yes, you guys are very correct. The absolute risk reduction is 5%, and this is, you're just subtracting one number from the other. So the difference, as we said before, is 5%. And here's the final question from this data. Which of the following is the number needed to treat?
Okay, releasing poll in 5.
So I'm going to answer another question in the meantime. Do you need to know the incidence to calculate the risk ratio in all studies, cohort, cross-sectional, etc.? Any exceptions? I mean, in general, a cross-sectional study, because you're taking a cross-section, that is just a slice in time, you won't be able to infer from your data what the incidence is, because it's only a snapshot. You can only understand the prevalence. I've just taken a picture of the barrel. I don't know what's coming in from the jug. Now, so you wouldn't be using a risk ratio in a cross-sectional study in general. There aren't really any exceptions to that rule. You just have to know the incidence to calculate the risk ratio. I can't really think of any exceptions. There might be some other statistical methods to get around that barrier, but if they are, I don't know them.
Okay, ending poll.
Okay, so we've got a couple of answers here, but the majority went for D, and I'm pleased to say that that is actually the correct answer. And I think every single medical school exam that I've sat has had a number needed to treat question. So I think this is a really important point to know how to calculate. So why do we care about the number needed to treat? It's because even though we're reducing your relative risk with the azenapenine by 25% and your absolute risk by 5%, we do not, we need to treat 20 people just to save one person, which is signified here by the number needed to treat. And the easy way of calculating the number needed to treat is by dividing 100 by the absolute risk reduction. So we already calculated here that the absolute risk reduction is 5. So you divide 100 by 5 and you get 20. If this went from, let's say, 20 to 18, the absolute risk reduction would be 2. You'd divide 100 by that 2 and you'd get 50. So it's very easy to calculate, and it's a medical school exam favorite. Please make sure that you understand how to calculate this. And just to philosophically understand why this is important, it's more to do with like, okay, so if I just graph out the data from the study, the azenapenine, as we said, 25% less deaths as compared to controls, and the absolute risk reduction is 5%, as we said, when we look at it in total. But the thing is, what about the people that were going to survive? So with the controls, 80% of people survived, and with the azenapenine, 85% of people survived. And actually, if you think about it, that of those 85% of people that survived on azenapenine, actually 80 were going to survive anyways. So for those 80 people, we haven't actually we haven't given them any benefit. We've only benefited that extra little top here, the 5% that were otherwise going to die. And you might still think an extra 5% of people living is great, and I do agree. But when you think about sort of more on a public health perspective, it could be that azenapenine has massive side effects, or it could be that it's really expensive. So you have to know what proportion of the people that were gonna survive anyways you're giving this extra drug for no reason, really. And obviously the dream is figuring out how to identify this extra 5% and only give azenapenine to them, but you know, that's another story. How does excess, I'm just answering a question, how does excess risk fit into this? When you say fit into this, do you mean the number needed to treat? Is that what you're going for there? I'm not sure. Could you just clarify your question? And another person asks, so what would the ideal number needed to treat be? There's no ideal. You want that. You basically want it as close, like as small as possible. So if possible, you know, every single person that you treat was gonna otherwise die. So what tends to happen when you introduce a new treatment, let's say before antibiotics, you know, loads of people would just die from infections, and then you introduce antibiotics by, you know, Fleming, and then loads of people that were going to die don't. So obviously the number needed to treat is like really, really small because there was no treatment before. But then when you're comparing between different antibiotics, maybe the difference isn't that, there might be a more modest difference. But that still doesn't mean that improving antibiotics isn't worthwhile. So that there's no ideal number needed to treat. Absolute relative risk. So with absolute and relative risks, excess risk. So when you have a study and you're looking at different interventions, sometimes one intervention will increase your relative risk by a certain proportion. And when you subtract that from the baseline, that is your excess risk. And I know that sounds a bit conceptually complicated, but what effectively you're saying is how much more risk for a specific event or outcome is there with your specific intervention, or it could, if you're looking at a risk factor, it could be with your exposure, if that makes sense. But in the cases of what here we're looking at interventions is what is the increase of that risk. I hope that makes sense. Please do tell me if it doesn't. Um, is everyone good with the risks, the absolute and the relative, the number needed to treat? If so, we'll go on to SBA 9, and you know, guys, we're probably going to be done in the next 10 minutes, so we're almost there. This is a forest plot, and again, this is another medical school exam favorite.
Fifteen seconds. Okay.
Okay, so we are looking at the results right now, and the majority of people have gone for B, with a few people having gone for C as well. Okay. Okay. I can see that. Okay. So the answer here is 2, as in B. And I'm just gonna go through, you must understand how forest plots work, because this comes up in exams all the time, and it's also something you might get in OSCEs as well. It's something that we definitely get. So this is actually quite a simplified forest plot, and we'll look at a more complicated one in a second, but just the basics here. So each one of these shapes here, the boxes with the lines, represents a specific study. Normally they'll have a name here, so it'll be like Smith 2015 or Roy et al 2010, etc. And each one of these boxes is the overall outcome of that study. These lines here represent the confidence intervals of those studies, while the box itself is the actual risk ratio derived from that study. So going back to the things that we learned earlier, if the confidence interval of a specific study intersects the number 1 when it comes to risk ratios or odds ratios, it means that that specific result is statistically insignificant. Before we were talking about specific risk factors, here we're talking about studies, overall studies. So the overall result of study 1 intersects number 1, this line which represents number 1. So irrespective of what this box is and how big the line is or where this is not statistically significant. Neither is study 4. The only studies that are statistically significant are 2 and 3 because their lines do not touch 1. This rhomboid shape here represents the overall results of the meta-analysis. That's why it's a different shape. This is not primary results, sorry. These are the results of the meta-analysis from the meta-analysis authors. Is everyone on board with that? And I'll answer some more of the questions after I've just finished with the forest plots. So what is a meta-analysis? I think you all know. You just take the results of multiple studies and you put them together to increase your statistical power. What is the significance of the boxes? So the bigger the box, so the reality is that this is a slightly poor design of this forest plot, but basically the bigger the boxes, the bigger the spread of the variables that they tested. Typically in proper meta-analysis, the boxes tend to have a standardized size, but yeah, the bigger the bigger the box, the more wide the spread of the variables were in the distribution of that measurement. So let's say if we're measuring height, then the population, like the tallest and the shortest person, if that makes sense. I hope that answers your question. So yeah, the distribution of the measurement within the sample, whatever it was that you were measuring. So yeah, and the idea of a meta-analysis is to increase statistical power. And even though, you know, the studies are only as good as the sum of its parts, it does increase the statistical power. So it's probably like the highest level of validation for a hypothesis. So I did mention on heterogeneity of studies. So sometimes, you know, as I said, some studies have incidents, some studies don't. Some studies might only test Afro-Caribbeans, and you start introducing biases into the meta-analysis, and this is really important, and this is one of the struggles that meta-analysis authors have. And there are various statistical tricks that you can use to remove those biases, but you know, that's kind of beyond the scope of this lecture, but just be aware of that idea. And this is just to show you how complicated proper forest plots can be, and just to not get confused, it's still these rhomboids are the sort of collection of results. The lines and the boxes still mean the same thing. It's just in the case here, you have the odds ratios, the confidence intervals in these brackets, and they've added a weight onto each of the studies. Stephen says, I thought the bigger box means the specific study is given more weight because yeah, I mean, I kind of wanted to avoid talking about weight, but yeah, the bigger the box, the bigger the weight. But the reason why you give a specific study more weight is because of the population size and the distribution of the variables within that study, if that makes sense. So a study that has the higher weight means that the statistics are skewed towards in favor of that specific study, so it contributes more to the overall result, if that makes sense. It's not just an average, if that makes sense. I'm sorry, Stephen, if the way I phrased that caused any confusion, but you're absolutely right. It is bigger weight, bigger box in that sense. But the reason you give a study more weight is because of the distribution of the variables, if that makes sense. Yeah, I'm sorry if I confused anyone with that. I think that is the answer to those questions. So could you define the relative risk reduction, absolute risk reduction, and excess risk again? Okay, Chinello, I hope I'm pronouncing that right. Can I just do that at the end? I'll come back to that question. Let me just finish up these bits and pieces on the study design, and I'll come back to that in the end. I haven't forgotten you. Oh yeah, and this is just an annotation just for your own perusal later on of the various factors in the meta-analysis. So you can just pause that and have a look at the different bits and bobs. Please don't get confused. At the end of the day, typically the information you need to extract is there. It's just, it looks more complicated. So now we've covered most of the stats. I want to spend a little bit of time talking about study design because they tend to ask questions on this quite a bit in medical school as well. These questions are more kind of like knowledge, you kind of know it or you don't kind of thing. But let's go on to this SBA, and we should be done in the next few minutes. So we're definitely not overrunning.
10 seconds.
So the vast majority of people here have gone for RCTs. And yes, this is just one of, this question comes up all the time. RCTs are the gold standard for drug or intervention investigation. It just is what it is. A lot of these other things have, we'll go through what the different studies are. Anyways, afterwards. Next question. And while you're looking at that question, I'll answer the next. Okay. What's the difference between epidemiological studies and clinical studies, and what is clinical epidemiology? So epidemiological studies, I mean, this is a semantic differentiation, but the idea is that epidemiological studies look at what's going on right now. So I'm going to go into the community and see how many people have HIV or how many people get colds. Whereas clinical studies are more to do with introducing a change. So I have a new drug I want to investigate, or I have a new test for the disease that I want to investigate. Now, clinical epidemiology is specifically looking at how these interventions affect the disease spread, if that makes sense. Because you could have epidemiological studies actually with other random stuff like opinions or how happy people are with their GP, you know, these kind of things. So, but they're never going to ask you to define those things in the exam. But overall, epidemiological studies are what's going on right now. Clinical studies are to see what happens when I introduce something, a drug, an intervention, whatever. Can we have the poll?
Last 10 seconds.
Ooh, we have a split. Okay. Oh, let me not do that. So the answer here is cross-sectional. And I can see why this caused some consternation amongst you guys. Because I think there tends to be a bit of confusion between these two types of studies. And I think the key things you have to think about is when it comes to incidence, right? You're looking at cohort studies. When you're looking at prevalence, you're looking at cross-sectional. Those are the two associations. And the question here is asking you, how common are herpes simplex virus? It doesn't say how many new infections, it just says how common. So this is asking you for prevalence. And therefore, when we're looking at prevalence, we're doing cross-sectional. Here's just a summary of the various study types. The main ones, I would say the main 5 ones, these are basically the same thing, the interventional. These could also kind of relate to the distinctions we made about epidemiological and clinical. Most of these studies here are epidemiological and most of these studies here are clinical, but there is some overlap. You need to understand these 3 types, how cohort is when you take a group of people and then you follow them through time to see what happens, whereas cross-sectional, you're looking at a point in time to see what the situation is. Case control studies are slightly different. This is when you take a group of people with a disease and a group of people without the disease and then compare them to see what's the difference. It doesn't really give you much information in terms of intervention or anything, how it changes through time. you really, really need to know about these two, the RCTs and the cross-sectionals, because you get so many SBAs on these. So randomized control trials, gold standard for drugs and interventions, cross-sectional, specifically used for calculating prevalence. And this is, I think, the final SBA before we pack things up.
Okay, 15 seconds remaining. And 5 seconds.
Okay, the vast majority went for selection bias, with a few other answers for the other bits and pieces. And you guys are very correct. And, you know, here I have a list of different biases that I think you do need to be aware of for both medical school exams and life. And I'll quickly go through them. So I'm just going to answer a question. Is confounding distinct from or a type of bias? Why is it emphasized so much? I don't understand why people get confused with confounding. Anything that is a bias is confounding because you're confused. It means that, like, okay, so here it's more of a distractor. Confounding just means not giving you the right result for various reasons. Bias is a type of confounding factor. That's all it is. Why is it emphasized so much? I don't know. I guess trying to trick medical students. I'm not sure why it's emphasized so much. So yeah, you can have biases in the way you study design. You can have selection biases. You know, maybe you only invite rich Caucasian people to your study. Response bias is when people, certain people are respond. This is especially important in like questionnaires and stuff like that. So there's bias in the way people respond. Measurement bias is a whole range of things, but it's just if there is a bias in the way you're measuring your outcome. Things like recall bias, for example, if you're asking people what they ate for breakfast, people are always going to say something less than they did. They're going to forget to tell you about the Kit Kat they ate. Observer bias is when you're watching the results, so you're inclined to only notice the good things that fits with your hypothesis. The Hawthorne effect is when people behave differently because they're being observed. So if you tell people that you're putting them on a study when it comes to like the amount of calories they eat, they might stop eating that kebab on the weekend. And resentful demoralization is when people drop out of a study because they're angry at the fact that they've been given the placebo. Confirmation bias is when, as I said, you're looking to validate what you believe in, so you ignore things that are contrary to your beliefs. And publication bias is when you're trying to, you structure your study in a way that makes it more publishable, rather than looking for the truth, because certain things aren't fashionable in science, so people don't investigate them. So that, if anyone wants any of these biases explained in more detail, I can do at the end. But that pretty much brings us to the end of my presentation. As actually I didn't mention, I'm one of the people who are part of the Study Hub team, and I just wanted to kind of direct you guys towards some of our resources.